Welcome to part 2 of this tutorial on OPV devices. In part 2, we will discuss the two most widely used device structures for OPV devices, and then we will talk about the current voltage characteristics of OPV devices, and we will continue with the explanation for the power conversion efficiency of OPV devices. So in this part of this tutorial, we will describe the typical OPV device structure. There are two widely used OPV device structures, and that is because of what we just said. There are small molecule materials and there are these higher molecular weight polymeric materials. So what we are seeing in this slide is a bilayer OPV device structure. This structure is commonly used for small molecule OPV devices. So for example, if we use copper phthalocyanine as a donor and the C60 as an acceptor, we can build up the OPV thin film device by using this kind of structure. So we can start with a sheet of glass which has been deposited with the transparent conducting oxide. Notice that part of the transparent conducting oxide has to be etched away so that we can make an electrical contact at the end. On the transparent conducting oxide, we put down or we deposit the two layers. So we deposit the donor layer first, to be followed by the acceptor layer. And finally, we deposit metal. And typically, this will be metals such as aluminum. And when we use this device to generate electrical power, what we do is we shine sunlight from the bottom through the glass sheet and the transparent conducting oxide. And the photovoltaic or PV effect will take place at the junction or the interface between the donor and acceptor. And as a result of that, you will get a voltage between the cathode and the anode. Notice that the device active area is basically the area where the current which is generated can be collected by the device. In other words, the red and the blue regions, which are outside the two dotted lines, they do not contribute to any electrical current because they are too far away from the active area of this device. Next, we will talk about the bulk heterojunction OPV device structure. This device structure is more important because it is what is widely used in industry to fabricate photovoltaic device for real applications. The bilayer structure is more suitable for research and development only. So we will explain more about the bulk heterojunction OPV. So as you can see on this slide, there is just one layer, the red layer, between the transparent conducting oxide and the metal electrode at the top. However, inside this red layer, there are actually it's actually as a mixture of the two components, the donor and the acceptor. And this is because this bulk heterojunction OPV structure is more suited for solution processed polymers. In other words, we can dissolve the polymer donor material and we can dissolve the acceptor material as solutions. And then we mix the two solutions together and we can deposit the mixed solution in one step as the active layer. We can use spin coating method or we can use a printing method, and you can do this over a much larger area than possible with the bilayer device structure. So because of this, the active layer, the absorber layer in this structure is actually what's called a nanocomposite. And we have an experimental image of this kind of bulk heterojunction on the top left. This is what is called an atomic force microscope, AFM image. And the two components are P3HT and PCBM. The difference in contrast in this image is due to the interpenetrating network of the P3HT donor and the PCBM acceptor. And the PV effect is taking place at the interface between the two components. So one thing which is important to point out is that only those excitons which are within a short distance from the interface can be converted into electrons and holes. And that is why we need to have this interpenetrating network. So in this part, we will explain the OPV mechanism. This means how we can convert sunlight into an electrical current by using the two device structures which we have seen. And we do this by using 4 schematic diagrams. These are what we call energy diagrams. The horizontal lines you see on this slide and the next one represent energy. They are called the energy levels. And in any organic semiconductor, there are 2 important energy levels. The lower one is called the HOMO, or the highest occupied molecular orbital. The upper one is called the LUMO, or the lowest unoccupied molecular orbital. And you can see from these diagrams that in between the LUMO and the HOMO, there are no other energy levels. And this is because this is the energy gap. It's a property of any semiconductor. The light from the sun consists of discrete photons. If the energy of the photon is greater than the energy gap, then optical absorption can take place, because the energy of the photon can excite an electron from the HOMO to the LUMO. And this is illustrated on the left of the first energy diagram. After the photon absorption, it will immediately lead to the next event, and this is called exciton generation. So on this diagram, you can see the electron has formed a so-called bound state with the hole indicated by the dotted line, and this is called an exciton. This exciton is a neutral excited state. It's like a hydrogen atom. So it consists of an electron and a hole, and once the exciton is formed near the surface of the OPV device, it will diffuse to the interface between the donor and the acceptor. This is because of the concentration gradient, and the diffusion is indicated by the red arrow on the right-hand energy diagram. Now we look at the third and the fourth stage of the OPV operating mechanism. In both the bilayer device structure and the bulk heterojunction device structure, the exciton will eventually arrive at the interface. On the energy diagram, this interface is represented by the vertical line between the donor and the acceptor. And you can see that there is an energy step. Okay, so the LUMO of the donor is at a higher energy than the LUMO of the acceptor. And this is important because when the exciton arrives at the interface, the electron will undergo a jump, illustrated by the arrow, to the LUMO of the acceptor. Once this process has completed, the exciton has split, or they call it dissociation. After exciton dissociation, we basically have a hole in the donor and an electron in the acceptor, and they are free to move. So then we have the last step, which is charge transport and collection. So by charge transport, we mean the electron in the acceptor will move towards the cathode electrode, and the hole will move through the donor towards the anode electrode on the left. And by collection, we simply mean that these two charge carriers will arrive at the respective electrodes, and they become available to the external load. So starting from the first step to this last step, we can see how a photon of light becomes converted into an electron and a hole at the external terminals of the OPV device. So in this slide, we show an actual experimental OPV device. So this is fabricated in a university laboratory. So at the top, you can see the glass substrate And this is because we have to make an electrical contact to the cathode electrode. And in this case, we use aluminum for the top cathode electrode. The brown layer is the bulk heterojunction layer. So this shows the color of a mixture of P3HT and PC60BM. So notice that the color is dark because it is able to absorb the sunlight. And at the bottom of this glass substrate, the transparent layer is indium tin oxide. So this one is used to conduct the hole carriers, and it forms the second terminal of this device. The dimension of this device is about 2 centimeters by 2 centimeters, but the actual active area of this device is only 3 millimeters by 3 millimeters. So there are 4 of these devices, and the total area is 4 times 9 millimeter square. After an OPV device has been fabricated, we must perform a current voltage measurement under illumination. That means we use an equipment called the solar simulator to simulate the sunlight inside a laboratory. And what we do is we illuminate the fabricated device by simulated sunlight, and then we measure the current from this device as a function of the voltage. And the curve we get is called the current voltage characteristic. And this one shows a typical current voltage characteristic from an OPV device. First, we notice that the current density on the left is negative. That is because when the device is under illumination, it is behaving as a power source. So it is sourcing current. It is sending current out to the load, and we therefore represent that by a minus sign in the current. At the bottom of the left side, there is an important parameter for the OPV device, and it's called the JSC. This is the short circuit current density. It is the current density we can get from the device when the 2 terminals are shorted to each other. At the top of this current voltage characteristic is the VOC, or the open circuit voltage. This is the voltage across the device when there is no current flowing from the device. It is the maximum voltage we can obtain from the OPV device when it works as a power source. In between the VOC and the JSC, there is a third important point, and this one is called the maximum power point, or the MPP. Next, we talk about the most important device parameter of an OPV device, and it is called the power conversion efficiency, or the PCE. This PCE is important because it tells us how good is the OPV device in converting the solar energy into electrical energy. And this is the reason why we must carry out the current voltage measurement, as shown on the previous slide. The PCE can be found by using the first equation on this slide. What we do is we divide the product of the VOC, the JSC, and a third quantity called the fill factor. We divide the product of these three by the incident light intensity. This incident light intensity is basically the intensity of the simulated solar light source, and it is measured in watts per centimeter square. So how do we work out the fill factor or the FF? And this can be done by using the second equation. So what we do is we find the points, the maximum power points on the current voltage characteristic, where the product of J and V is a maximum. And then we divide that by the product of JSC and the VOC, and we will get a ratio called the fill factor. And this fill factor can be calculated on the previous slide by simply using the area of the two rectangles. So next we will show some very recent OPV PCE values. This is obtained from a consulting company, and we are showing the most recent data. So very recently, the PCE for both single junction devices and the inverted devices have reached about 9%, 8 to 9% range. And for the so-called tandem device, where we stack two or more single junction device, the PCE has exceeded 10%. Notice that all the efficiencies which are listed here are measured independently by standard laboratories. So they are what's called the certified PCE values. They are done under very strict procedures using standardized conditions. One interesting observation is that in the last about 2.5 years, the efficiency values have jumped by about 50%. And for those working in this industry, the widely accepted target for commercial application is 10%. So we can see that right now we are already at that critical point. And further improvements in materials, say the donor or the acceptor, can push these values even higher. So here we summarize the main content of this tutorial. We have explained the operating principle of OPV devices. We have also explained what are donor and acceptor materials in these devices, and we have introduced some important examples of these donor and acceptor materials. And thirdly, we have discussed the electrical characteristics, the current voltage characteristics, and the power conversion efficiency of PV devices. The power conversion efficiency is the important performance parameter for these PV devices.